So, we talked about potential energy. If the force acting on the particle is conservative, the resultant force, the only force, then we can define this potential energy function V, and then V plus kinetic energy, this is constant. We call it law of or principle of conservation of energy. And how we define this V? Remember that F dot dl integration from a point A to B. Now, I can talk in terms of point A to B, because this is conservative force and path is not important, only the end points are important. This we define as V1 or VA minus VB. So, if you have just a small displacement dl, you can say this F dot dl is small change in the potential energy, and that is here minus dV, because it is initial minus final, not final minus initial. So, it is minus of a small change in potential energy, and this is it. Now, this gives me another beautiful equation. If I write in component form, this will be Fx and dl is dx. So, dl you can write as dx I cap plus dy j cap plus dz k cap, and f you can write as fx I cap plus fy j cap plus fz k cap, and if you take the dot product, it is fx dx plus fy dy plus fz dz. So, this is fx dx plus fy dy plus fz dz, this is dV. Now, if you take this y and z as constant, which do not change, only x changes, then you have fx dx is equal to dV. That means fx is minus dV by dx minus. This is this minus here. Fx is minus dV dx, provided dy is 0, provided dz is 0, y is constant, z is constant, and that is the partial derivative of v with respect to x. So, fx from this equation is minus del v del x, and similarly fy is minus del v del y, and fz is minus del v del z. So, if the potential energy function is known as a function of x, y, z, I can get the force components, and if the force is known as a function of x, y, z, then I can construct this potential energy function. Since only the difference is defined, so it will be arbitrary to the addition of some constant energy. So, with that much of uncertainty which you have to choose, where you take potential energy to be 0, you get this V from F and F from V. So, these are things. You can take some more examples, say u is equal to half k x square, not u, V. V is equal to half k x square, one dimensional motion. Entire motion is on the x axis. So, one dimensional motion, and if this is the case, then you know when it occurs. It occurs in your simple harmonic oscillations. Just in the previous lecture we talked about that. F is equal to minus kx. Okay, so if you plot this V as a function of x, x can be positive, x can be negative. So, if you plot this V as a function of x, it will be a parabola. It will be a parabolic function, half kx square. So, from this diagram you can work out, if you take the particle is here at this point, at this x, this is the origin. So, if the particle is here, then the corresponding potential energy is here, this is the point on the curve. This is the point on the curve. And here if you draw a tangent, the slope of this is del v del x, which in this case is dv dx, and therefore your force is all one dimension. So, Fx is same as F. So, that is minus of this dv dx, and that is minus of this tan theta. So, from this diagram also it comes out that if the particle is here on the positive side of the origin, then the slope is positive, this angle is less than 90 degree acute angle, slope is positive, tan theta is positive, and the force is negative. So, force is towards the origin. Whereas, if the particle is here and if you draw the tangent, then the tangent is like this angle is more than 90 degree obtuse angle, and the value of tan theta will be negative, and therefore, the value of x will be positive. So, if the particle is somewhere here, then the force is positive, tan theta is negative, force is positive. So, force is in this direction. So, qualitatively many of the features come from this diagram. So, the particle has to oscillate and all those. Then if you have a particular energy which is fixed, the total mechanical energy is fixed, and since this is in energy units, potential energy. So, I can find on this line what is the total mechanical energy of the motion I am interested in. And if this is that point, if this is that total energy u, this is that total energy u, then if I draw a line here, the total energy will always remain u. And if the particle is somewhere here, suppose the particle is somewhere here, then this is the potential energy, this much is the potential energy, this much is the potential energy, because this is the potential energy curve. So, as a function of x I am plotting potential energy. So, at this value of x, this is the potential energy and this is the total energy. So, this is kinetic energy, this much is kinetic energy, and kinetic energy plus potential energy is the total mechanical energy. So, now you can see if the particle is moving away from the origin, the potential energy is increasing, the kinetic energy is decreasing, the totals remains u. And if the particle reaches this point, this particular point here, call it x equal to a, what happens? This is the potential energy and this is also equal to the total energy, mechanical energy, and therefore, the kinetic energy is 0. So, the particle comes to rest at this position, the kinetic energy is decreasing, here this much was kinetic energy, then as it moved to the right, kinetic energy decreased, further decreased, and finally, it became 0. So, the particle is going away, slowing down, and then it comes to rest, and then it turns back because the force is there. So, this is the turning point, this is turning point. From here the particle has to turn, and once it turns, it comes towards the origin, kinetic energy keeps on increasing. Here the kinetic energy is same as the potential energy. So, the same as the total mechanical energy, and so the potential energy is 0. But then since it has kinetic energy, it is moving towards left, it keeps moving towards left, it reaches somewhere here, then somewhere here, then somewhere here, and finally, at this place which is minus a, when it reaches here, once again the kinetic energy is 0. So, this is also turning point. So, these kind of analysis you can do once you know the shape of this potential energy curve. Many of the qualitative features of the motion you can derive from this. Let me take one more example. Suppose you have a proton. and you have another proton, and suppose this proton is somehow fixed, somehow this proton is fixed and this can move, and suppose this is moving, this distance is large and it is moving towards this first proton like that. It has some velocity v here, v naught here, and this distance is quite large. This distance is quite large. As a function of distance, what is the potential energy? You know that, right? If you have two charges q1, q2, the corresponding potential energy is q1, q2 divided by 4 pi epsilon naught r. So, V is equal to, let me say this is all x axis, the entire motion is on x axis. So, it is right heading towards this proton, and this I am taking as x axis. So, it will be proton q1 q2 by 4 pi epsilon naught and then x plus positive, both are protons. This is the potential energy as a function of x. If you plot, what happens? If you plot, it will be a hyperbolic curve. It will be a hyperbolic curve, and then initially it is at a large distance, and then the speed is v naught. So, initially whatever you call t equal to 0 or so, initially r is or x is large, very large, and the kinetic energy k is half m v naught square, and this is also the total energy, because for large x this potential energy is tending towards 0. So, this is the total energy known, suppose it is known, and that total energy is somewhere here, let us say this is that total energy, and initially x is very large, that means the particle is somewhere here at a large x, but the total energy is this much. If the particle is here, the potential energy is almost 0 and kinetic energy is, so this much is the kinetic energy and also total mechanical energy. Now, the particle is coming towards this proton, so x is decreasing. So, x is decreasing, particle comes here, here, suppose it has come here. When the particle is here, then this is the potential energy, this is the potential energy, that is the curve I have drawn, potential energy versus x. So, this is potential energy, total energy is fixed, and therefore, kinetic energy is this much is the kinetic energy, decreased, right, because it is repelling. So, the speed will decrease, kinetic energy will decrease, kinetic energy is decreasing, and the particle comes here, some x naught, and then you are on the curve, you are reaching this point. So, the entire energy is potential energy, the kinetic energy is 0. This is turning point, the proton turns from here. So, it comes and at some x naught it turns, and once it turns, that is it, there is only one turning point, it will not turn again, it will go to infinity. Now, this description is relevant for fusion in sun. You can set up your coordinate system with origin here and then do some algebra. It is almost the same problem. In this particular frame, it is moving only in x direction, this is at rest. So, almost similar mass you have to, if you want to do the real quantitative analysis, then you have to do something else, because it is a non-inertial frame, remember, if you put your origin here. So, we will take care of that, but essentially this is the case. The separation between the proton will be having a value x naught, which will depend on the initial kinetic energy. Now, in sun the temperature is some T10 to the power 7 Kelvin or so of that order, and you can assume that all the protons are moving with some thermal energies, and that also you know the random motion 3 kT by m square root, that is the square root RMS value of the speed, and if you calculate this you get some value, and with that value you can calculate how much should be the x naught. Different protons are of course moving with different velocities. Different protons are moving with different velocities, but this is the average kind of thing, some kind of root mean square. So, if you take this as the velocity, calculate the kinetic energy and find this x naught here, that x naught turns out to be some few hundred femtometers, say 300 femtometers. Okay. The story is that this is not a complete picture, because protons also exert nuclear forces which come into play once the separation is of the order of femtometers. So, on this scale I do not know where will be the femtometer. Suppose this is femtometer, 2-3 femtometers. So, if you are inside this, if the separation is in femtometer range, then on top of this Coulomb potential energy you also have potential energy corresponding to that attraction, nuclear attraction, and that is very strong in femtometer region. So, this curve actually goes like this. Okay. So, this is the nuclear attraction range where the potential energy has sharply gone down. The Coulomb potential energy is increasing, but it is sharply going down, and it overtakes this Coulomb energy, and final potential energy is of this type. So, if proton and proton are to fuse, fusion reaction is to take place in the core of the sun, the first thing is that 2 protons should fuse, and after that more protons will add to make a helium nucleus. But the first stage where proton and proton have to fuse, it must come closer to this separation. Okay. So, it must reach somewhere here, but then x naught is 300 femtometer and this is 1 or 2 or 3 femtometers. So, this is 300 femtometers. Okay. So, even if you say that you have some protons which are of higher than this having speed higher than this RMS which we calculate from here, even then you do not have enough protons to reach here, fuse and give that wonderful energy that we receive from the sun. So, then there are some other phenomena, barrier tunneling and all those things, quantum mechanical phenomena, which finally gives us required number of protons actually reaching here and then fusing and creating that energy of the sun. Okay, so these are the things that you can do with potential energy. We will come across such things again and again. And now I want to introduce another parameter. So, we talked of linear momentum, we talked of potential energy, and then from there this total mechanical energy, kinetic energy. Another parameter which is important in mechanics, and that is angular momentum. So, when we say angular momentum, generally what comes to your mind is something is rotating, and angular momentum should be some moment of inertia times angular velocity. So, it should be a rigid body or an extended body, but even for a single particle this angular momentum concept is very useful. Let us see how. Angular momentum is basically angular momentum is defined for a particle only, and if you have extended bodies then you add angular momentum of all those particles to get the total angular momentum, but the basic definition is for a particle. And what is that? The first thing is this angular momentum of a particle about a given point, which I will call origin. So, the angular momentum of a particle is also associated with which point you are talking of. Particle may be somewhere else, but this point is you have to choose somewhere. Okay. So, for linear momentum it does not matter where you have taken your origin or what, it is mass of the particle, velocity of the particle, local phenomena. But angular momentum, particle is needed, the parameters of particles are needed, we will just see, and then the origin or the point about which this angular momentum is to be calculated. So, definition includes this point, and that is given by, we write it L with a vector sign, this is a vector quantity, and this is r vector cross p vector. What is r vector? Is the position vector of the particle from the chosen origin, this point, this given point, from that given point. And p is the linear momentum of the particle. So, if you have an origin, if this is that point, and then at certain instant you have a particle of mass m and is moving in some direction, say this direction, this particle of mass m is moving in this direction with a speed v, the angular momentum of this particle at this instant about this point, always whenever there is an angular momentum, which point, about which point, so that should be known, and that is from this origin you join that particle, okay, call that vector as vector r, construct this mass times velocity here, and then take cross product of these two. In this diagram, if this is x axis, this is y axis, then this r cross p, p will be in this direction, will be going into the board minus z direction. So, angular momentum is a vector quantity, it has a magnitude, it has a direction, and the direction is perpendicular to this r vector and perpendicular to this linear momentum vector. So, that is angular momentum defined about that particular point. Okay. Correspondingly, and the magnitude of course is mass times velocity and this distance r m v r, and then the angle sine of the angle between two. So, this is r vector, this is that p vector, this angle is theta. So, sine of theta, r magnitude of this r vector, magnitude of this momentum, linear momentum vector, and then multiplied by sine theta, that is the magnitude. Correspondingly, there is a similar quantity or similar looking quantity that also we define, torque of a force. Once again about a given point. Which we will take as the origin, and that is written as tau vector, we read it tau, T-A-U, Greek letter tau, and then the vector sign is equal to r cross f, and once again F is the force, you want torque of a force. So, where is that force? It is here and about a given point. So, you have a given point and from that given point to the point of application of force. Force is acting on some particle, so position vector of that particle or position vector of application of this force. So, that is known as torque. Once again the similar story, it will be perpendicular to this r vector, it will be perpendicular to this f vector, and along that perpendicular this side or that side will be decided by the rules of cross product. You know how to get the direction of this cross product, and the magnitude will be once again r into f into sin theta, similar picture here. So, that we define as torque. And very interestingly, if you use this L is equal to r cross p and differentiate with respect to time, dl dt, that will be r cross dp dt and plus dr dt cross p. Now, dr dt is velocity vector and this p is mass times velocity vector, cross product is 0, and this is dp dt is f. So, it is r cross f. That means torque is equal to dl dt. For a single particle we get this equation, very simple equation, torque is dl dt. If you have a single particle, some force F is acting on it, you have chosen an origin, and from that origin you are calculating angular momentum as a function of time. The particle is moving here, there. So, the position vector is changing, speed is changing, direction of the velocity may be changing. Calculate how much is this dl dt, that must be equal to that r cross f, which is torque. So, we will take from here.